that you guys probably have never worked with them. So what I like to do is to start with the actual words there, figure out what in the world does it even mean. Well, what's a function? Conjunction, junction. No? All right. How would you define out a function? I know you guys have all done this. You did this whole thing way back in your algebra classes when you looked at functions. How do you tell whether or not something is a function? Don't you what? What is it? The thing with I know what you're talking about. I know what you're talking about. You're talking about vertical line stuff. So when I'm looking at a function is defined by any. Actually, I don't want to write this right. Any equation such that, not suck that, but such that there exists exactly one element, getting fancy on you here, in the domain I should say there exists this should be for every element. Sorry, this should be for every element. Sorry. For every element in the domain, there is exactly one corresponding element in the range. So I went as absolutely long-winded as possible on that to see if you can make sense of it. Yes, ma'am?
Did you do that to make me angry?
Yes.
Like you capitalized all those letters that are not supposed to be capitalized?
Assuming. Ooh. What? It's feisty. It's warm in here. Domain and range. Going back to that. When you're talking about domain and range, what are the values of your domain? Think about it for a second here. I'm asking a lot now.
All real numbers.
It could be, or it could not be. What comes first in the alphabet, domain or range? Domain. So will the domain correspond to your x values or your y values?
Your x values.
Because x comes first in the alphabet.
Yes.
So your domain is going to be the values of x on a graph. Your range is the values of y on a graph. So what this is saying, for a very long-winded version, for every value of x, there exists one value of y. And that's what you guys were talking about, that whole vertical line test. Because when you start to look at, in terms of ordered pairs, if I'm looking at ordered pairs, let's say it's -2 and 6, 5 and 3, 1 and 7. Be it.
Wow.
Yay!
If I look at something like that, for every value in the domain, for every x value, is there exactly one value in the y range?
Mm-hmm.
Yeah, the y values are not repeated. Therefore, this could show that it is a function. Whereas if I take a graph, and I know you guys were talking about this a second ago, that whole vertical line test. As you go through this and I'm looking at it, these two, well,
It's the thought that counts.
I'll make this one a little bit bigger.
Same.
Whatever. Those two wind up being a shared value vertically. Therefore, this x coordinate, whatever it might be, let's say it's -3, That -3 is in two places at once. Can that happen in a function?
No.
No. So this means that this is not a function, whereas something like this is a function. What about this? What's that? It's a parabola. Is that a function?
Yes.
Yeah.
I was gonna say.
It's a parabola is a function when it is an x squared parabola. Wait,
Oh, wait, there's more.
what's that? It's a y squared parabola. That's a y squared parabola. Is a y squared parabola a function?
No.
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 No. Circle is not a function because it won't pass the vertical line test. Okay? Yes,
I
sir.
mean, if like.
Okay.
Hold on.
Okay, so there's this magic trick that you can use to find out if something's a function.
Right.
But what does it really mean?
What do you mean?
Well, just because it fails the vertical line test doesn't necessarily mean.
The reason I see where you're going with that. The reason that this is going to fail the vertical line test. Let's just say your axis is here. At 1, it's at 1, -2, and 1 in 5. Go back to the pure definition of being a function. For every value, or for every element within the domain, in other words, any x value, there exists exactly one value in the range. Here, I can't be two places at once. That's what it means. Can you be two places at once?
No.
There you are.
Well, I mean, with modern day cloning technology.
We're getting there. That's what that means. Basically, that vertical line test is a short way of looking at it as if I hit 2 points at the same time vertically, I'm not a function. That's all it is. It's just a shortcut way to show that it works. That's all.
I also wouldn't function if there was a
Okay,
closed.
so it works because if there were 2 points, there can't be 2 points on 2 separate places if it's a different equation, so it wouldn't be part of the same function.
What happens is, you're getting lost, I think you're getting lost in the terminology here. When you have any equation, if that value of x generates 2 different values of y, it's not a function. Think of it this way. What's the square root of 4?
16?
Square root.
Give me a second.
It's not a trick question.
It's 2. It is 16. What are you talking about?
What?
The square root.
4 squared is 16.
No.
The
Square root.
It's not a trick question.
Again, what are 2 numbers that you multiply together that are the same number that gets you to 4? 2 and 2 or -2 and -2.
Yeah.
So what I'm saying here is it doesn't wind up being a function then. Okay? That's all. So what we're looking at though, back to where we're at, we're talking about these things called piecewise functions. And if you think about piecewise function is just pieces of functions. That's it. What you're looking at here is that these are going to be domain-dependent graphs, domain-dependent functions. What I mean by that is that the values of x can change what the function looks like. Take a look. If I have this, just by looking at the graph, we're not drawing it, just looking at it. When I'm looking at it as it's going from left to right, it's an increasing function. You guys agree on that?
Yes.
There's a positive slope. If I'm looking at this portion here, it appears I have a slope of 1. Up 1, right 1, up 1, right 1. We okay on that?
Yeah.
So as it's increasing from -infinity to 0, it has a slope of 1. What happens at 0? It changes to 2. So the slope changes at 0. So this graph is dependent upon the domain because the equation changes. The equation changes as the domain shifted. So you get 2 different equations. Another one that's very obvious to look at is something called a step function. Think about insurance rates. Male insurance rates when you're 16 are a lot more expensive than they are when you are 30. Think about ticket prices. From 0 to 3 is free. From 3 to 6 is $5. From 6 to 10 it's $8. From 10 to 15 it's $15. The graduated prices, that is a step function. It is dependent upon your age as to what you're going to spend for something. I know you've all seen that before, right? When you're at, like, what's that?
Castlevania tickets. They're different prices for different
Yeah, exactly.
You should buy one.
Nice. The, you look at it, things like that. Depending upon what time you buy something. My wife registered to run a half marathon. It was X amount of dollars up until Monday. At Monday for the next month, it's so many more dollars. After that, it's so many more dollars. So it's graduated through that. It's a step function. It's a piecewise function. The domain, the time frame, changes to what the output is. Does that make sense? So what you're going to be able to do then is work with things like this. And obviously this is a long-winded version of what I just said. A piecewise function is just some combination of equations that wind up being domain dependent. And you did problems like this in the past when you first looked at what's called function notation. Remember when you did function notation, where you'd have an f of x equation or a g of x equation? At some point in time, I know you've done it, and then it's going to ask you this. What is f of 0? Well, you've got two sets of equations. You've got an f equation and a g equation. If I'm going to ask you what is f of 0, which one do you think you're going to use? The one with the f. Now, what you're doing then is, first of all, this says, hey, use the f equation, dummy. So, you use the f equation. This says, pick one. Which one are you going to pick? It's telling you that you're trying to find f of 0. So you are using the domain value of 0 to figure out what the y value is. What's the range value? You need to choose, well, which one of these does 0 go into? Is it going to be less than or equal to 2 or greater than 2? Which equation do you use? Yeah. So it's domain dependent as to which one you substitute in for. It is quite literally that. You are just looking to see where it falls. So f of 0 just winds up being, well, 3 times 0 minus 7.
-7.
Negative 7. Woo-hoo. You didn't need your calculator for that, did you? No. Sure? Just making sure. F of 2. Same idea. Which are you going to use, f or g?
Q.
No, you want to use f because there's an f in it. So don't f it. You want to use the f equation. Now, it's the end of the day, I'm warm. Which one do you use, the top or the bottom? The top equation again. I use the top equation because 2, last time I checked, is less than or equal to 2. So you get 3 times 2 minus 7. Negative 1. So that element in the domain, 2, generates the value of the range, negative 1. And that's all it is. What changes now? Nothing. You just pick. Yeah. All you're doing is just picking which equation. Shimki, what's wrong? All right. I saw the scrunchy face and I had to stop here. All right, let's go back to this.
So you just pick the equation that it makes sense in?
Yeah. What letter is this?
G.
Gee whiz, you're right. Which one do you choose, the f or the g equation?
The G?
Good. For g,
What a G.
5. You have to look at
G.
you have to look at it being domain dependent. It's dependent on now which one do you choose to substitute in. Are you going to use the top one or the bottom one? Good.
Why does it matter?
Because it's domain dependent.
I don't understand.
Once we do this, the graph of it,
But if-
you'll pick it up.
So you're saying if I put, okay, so if I put 5 in for the top one?
If you put,
If I substituted it in and then did it for the bottom one, I wouldn't get the same answer?
no, because if you choose 5, if I'm going to use x equals 5, I can't use it here because x has to be less than 5.
So literally,
It's restricted in the domain that you can't use 5 here because it's just less than. Here it's greater than or equal to, so I can use it here. That's all I'm looking at.
basically they just
Whatever you say, Murph Dog.
slap a rule onto the equation.
Yeah, if you want to think of that, yeah, it's very good. They're slapping a rule on the equation, and the rule is showing you the dependence on where it's going to go.
What?
Because what happens when we graph these in a little bit, you're going to see that you'll wind up at different parts on the XY grid. Okay? And then go to the other one, g of -4.
Oh.
Again, gentlemen, I don't want to talk over you.
I'm sorry.
When I'm looking again at the last one, it's g of -4. So I know I have to pick the g equation because there's a g in it. And then I just look at the -4. Which of the two equations does -4 give it a true statement?
I get it now.
It's the smaller one. What? The second equation? -4 is greater than 5?
But when you put -1, like x doesn't become positive? Or no?
Remember, when this is just direct substitution. But you're thinking ahead of the curve here. What you're worrying about, first of all, is that it has to match one of those. That matches first, and then you substitute it. That tells you which one to choose. That rule. This is the rule for the graph, for the function. I look at this equation, 3x plus 5, if any number is smaller than 5. Any x value smaller than 5. I look at -x plus 3 for any number bigger than or equal to 5.
So it's not your answer that has to be less than 5?
The answer is the range.
Oh.
I'm looking at the domain. That's why I was calling it domain dependent. These are the dependencies of the domain. This is what you're using for the
I
domain.
thought it was the answers had to be.
No!
No, honestly,
no,
that's
no.
what I thought too. Like, I
Okay.
was like, why?
Yes, sir.
So the answer we're getting is the range?
Yeah. Domain is the input, range is the output. You get -7.
Yay!
Math. Yes, ma'am.
I'm irritated.
We graph things a little bit differently. What I'm saying about this domain and range is that I'm using, these are your domain restrictions because it's the x value. This is the part of the domain that you're choosing which restriction am I using then.
I just want some time.
I'll show you. Okay, I'll show you. So when it goes off of this then, obviously it's just a lot of just direct substitution. The next step then winds up being graphing. So what I want you guys to do, I'm going to pass around a few of these. Grab like 2 or 3 of these because you'll use a sheet of them for some homework. 'Cause I've got like 4 or 5 graphs I think you'll do tonight. But that way you have some for your notes and some for your
My work doesn't consider the fact that I go to school.
So I want to start by looking at the graphs. Let me rewrite this.
Yep.
I want to graph something. Bracket. I went to college to learn how to draw Jay Leno's face.
Can you show us?
It's just a bracket. That's all it is. So I know there's a lot of spares going around, it's not a big deal. Here's what happens. Guys ready? Anyway, what happens here is we're basically going to graph two equations on one piece of graph paper. And then the easiest thing to do, until you get good at it, is to go back and erase where it's a false statement. Go back and erase the parts of the function that don't work, the restricted parts. So if I'm going to look at just this first one, f of x is x. Well, that's really, really easy to graph. What's the slope? 1. What's the y-intercept? 0. So all I have to do is start at 0 and walk the slope of 1. And go the other direction as well. So there's your equation of y, basically y equals x, or f of x equals x. Now I'm going to look at what the domain restriction is for that graph. It says x has to be less than or equal to 0. So can it equal 0?
Yes.
Yes. Which means I can keep a solid dot at 0. And what direction are numbers smaller than 0 for x? To the left of that or to the right? Left. So I'm going to connect all these for this part of the graph. And what do you think I'm going to do with the rest?
Erase it.
Go on. It's okay. It's okay. This is, now you know, you might want to use pencil for some of these. Right?
Wait, hold on a second. Hold on a second. I have a question.
Yes.
So the second equation though is x minus, like x minus 1 is if x is less than 0. So would that make like -1 be?
No, the second equation is greater than 0. I'll show you. Hold all
Oh
here.
yeah.
Hold on here.
My God.
So less than or greater than was always an open dot.
Okay.
Less than or equal to, greater than or equal to was always a closed dot.
How do you remember?
What do you got?
Basically, it's just an if then thing. If
Yeah, if you want to think of it like that, that's fine. Yeah. If x is less than or equal to 0, then you graph y equals x. It's kind of an idea. That works. Now I go to the second graph, and I'll change color so you can see it better. Again, I have a slope of 1, but my y-intercept now is at -1. So I start my graph at -1, and I walk my slope of 1. I know that my domain is going to be for everything that's greater than 0, so I don't have to worry about graphing the stuff to the left. But I do need to pay attention to what happens when x equals 0. For this second graph, should that be a solid dot at -1 or an open dot? It's got to be an open dot.
Oh my.
This needs to be an open dot here, and then it's going this direction.
Wait.
So basically what happens there is that you have, through the domain of when x is less than or equal to 0, the graph is f of x equals x. When x is greater than 0, it's x minus 1. It jumps, it has a break in it. There's pieces of both of those graphs that were being used. That's why it's a piecewise function.
I see.
Wait.
Yes, ma'am.
So if you don't know what x is, then you
Yeah, but these, you'll always have some domain restriction because it's a section. Okay. Otherwise, you're just looking for intersections. Yes,
Can
ma'am.
you explain to me why -1 is included in that part?
Why -1 is here? Why it's not included?
And why it is?
It is included because
Like,
it's
why'd
the
you graph it?
it's the y-intercept. So I start that graph at -1 and I continue on with the slope. The reason that it's an open dot, not a closed one, is because it's
Well,
greater.
yeah, I get that part.
That's all. I just start at -1.
Okay.
Yes, sir.
This is kind of off topic, but this was never like assigned as an assignment, was it?
Nope.
We just need to know it. Yeah? All right.
Thank you. Let me show you another one. Same idea. Two different graphs, two different functions. I have f of x is either going to be 2x minus 1 when x is less than or equal to 1, or f of x is 3x plus 1 when x is greater to 1. Now, back in third hour, a student had a really good suggestion of marking lightly on your graph where the boundary, if you will, changes for the domain. Does everybody agree that the boundary for the domain changes at x equals 1? What's the boundary restriction? At 1, right? Okay, so that means on x equals 1. Is x equals 1 a vertical or a horizontal line?
This way.
Vertical. So what this student suggested, which is a great idea, is to lightly put in just some vertical line at 1, knowing that that's where your jump is going to occur between the two graphs. Because this is giving you the boundary to pay attention to. Does that make sense? He just thought it was a good idea, just kind of lightly shade it in. You don't need to. It just, that way you remember that something's happening at 1, when x is 1. It's either greater than or less than or equal to and all that. But I'm still going to graph everything like I would normally. So if I have 2x minus 1, I'm going to graph that. Where do I start? Negative 1. And then I walk my slope up 2. I'm not going to worry about my solid or dotted lines at the boundary level yet until I get everything set. So what I did there was just kind of graph the idea of what 2x minus 1 would look like, aside from connecting all those dots. So then I just go back and look at that domain restriction. That domain is going to be restricted at x is less than or equal to 1. So what side of that vertical line can I erase? The right or the left? Correct. I can erase everything to the right of it because I am looking for this graph to be on the other side because x is less than or equal to 1, which is going to the left. The dot there at the 1, does it stay solid or does it become open? Solid. It stays solid. Does that make sense? Yes, ma'am.
Wait, you said
Great conversation. It's okay. Now I do the exact same thing with the 3x plus 1. The 3x plus 1, where do I start that one? At 1. I started at positive 1. And now I walk a slope of 3. Up 3 over 1. Up 3 over 1. 3 over 1. Do I need to trail it going back to the left? Correct. Everybody hear Shimkey on that one? No. I don't need to worry about, bless you, I don't need to worry about trailing it back to the left because I know already that that part of the domain has been plotted. So I can erase the dot at 0, but what do I have to change to that dot at 1? Just make it open. Now if you did use pen and you had to make that open, would I be terrible if you just did that? It's okay. It's all right if you overwrite it to make it a big circle. But if you've got an eraser, it's just a little bit better to see it. And then you just connect your dots going upward. So there's that boundary jump at 1. The rates change. Remember, think of it going, when you go to the movie theater, you've got $5 for a matinee, then all of a sudden at 5 o'clock it's $7. It jumps at a different time frame. It's the same idea. The rate increases at a different time. Yes, ma'am. You can graph lines, right? Then you can do this. Because this is just graphing lines, and you're erasing part of it depending upon what this tells you. That's fine. Please do. Sir?
How do you know the boundary line
Would be at 1? Because I'm looking at this here. Something changes on this equation at 1. The first equation is going to be only when it's less than or equal to 1. The second equation is when it's greater than 1. Nothing's changing if that line is over here at 7. But I do know that something happens when that line goes at 1. That's why I just put in that little dummy line there.
Just take whatever number's there.
Yeah, because this is your domain. The domain changes, or I should say the domain changes, but the range for the changes. I'll get this right eventually. The equation's going to change at that domain specific when it's changes. Yes, sir.
So like, when you showed us the step function, whatever you called it, does that mean it can be like more than 2?
Yes. And it's very, very, very easy to use. Step functions are a breeze.
So would that be like if there were 2 or 3?
You'll
like
see.
when you had the
You have
box
boundaries.
in between.
Yeah, exactly. That's exactly it. That's fair.
Like, what else, like the swing, or what do we have to talk
I don't know.
Yeah.
Yes.
So those descriptions,
Yeah. Mm-hmm. Yep. Let me show you another one. I love you guys are always worried about the worst case scenario right away.
Because we know it's just, we know that it's just gonna get worse.
Oh, just you wait.
Oh, no.
As soon as I think I'm
I believe they're, every time I try to get out, they keep pulling me back in, right? Now this one is going to look really weird when you graph it. Because look at the boundaries they're asking you to plot. They're asking you to plot the first graph between -2 and +6. They're asking you to plot the second graph between -8 and -4. So you're just looking at little chunks of it. There's not one singular space that it changes. Each one of these is only looking at a specific portion of the domain. So when you see this, you're going to do the same steps as we did earlier, aside from putting in that vertical line because there's multiple values that things are jumping at. I'm going to graph 2x plus 1. That's really easy. I start at 1 and I walk a slope of 2. And I go the other direction. There's my first graph. I start at the y-intercept of 2, and I walk, or excuse me, started my y-intercept of 1, and I walked my slope of 2. From there, now I go to my domain restriction. That graph is only going to be valid for the values of x between -2 and +6. So I start at my value of -2 for x, and I know that's going to be the lower boundary. That becomes an open circle because it's a less than. You okay with that?
Yes,
All
sir.
right. Yes, ma'am.
Do these work on calculators?
Not really. I can erase these other 3. I need to continue this graph to +6, but I think if I'm not mistaken, my graph stopped at 4, so I can just go up 2 over 1, up 2 over 1. I really do my best to try and give you guys, when we graph things like this, stuff that'll fit on a 10 by 10, if not a 20 by 20, because you can go by 2s. My bad that I forgot to change the domain restriction there. But you get the general idea of that, right?
Hoorah.
Good. What do you got? Huh?
Wait.
You okay? See how the graph stopped at 4 if we were off the grid? We just wanted to be off the grid. Oh, yeah, it stopped at 4 and 9. The next one would be at 5 and 11. The next one would be at 6 and 13, I think. So it just happens to be higher up than what the graph will show. That's all. So if it changed, this would just become an open dot, and you just connect all those through.
Never mind.
Is that what you're asking? That's all it is. Okay? That's all it is. What's wrong?
I'm just, I don't know, I feel like I'm not getting something that I should. I don't know what
You can graph lines, right?
it is. Yes,
You know what I mean by domain values, right?
yes.
Then this is nothing.
Am I overthinking it?
Yes. Yes, you are. Yes, you are.
Yes.
Because when you go to the second one, oh yes, you got it.
So if it goes off the grid like that, it's fine, you just stop it.
What the?
You all right? Second equation. Same basic idea. What's that?
If it goes off the grid like that, it's fine if you just stop it.
I try my best not to screw with you too much, okay? In the second equation, I have a y-intercept of 0 and a slope of -1. We okay on that? The only reason why I graphed going that direction is because I already read that my domain is going to be restricted between -4 and -8. So do I even care what the x values are greater than 0? No, it doesn't make any difference. So I'm looking at this graph only being shown between -8, which is here, open dot, because it's just a less than symbol. I can get rid of those two. And it's going to continue through, let's see, -8, -7, -6, -5, -4, which becomes another open dot.
That's -3.
Oh, was it -3? Oh, sorry, I missed it. There we
You
go.
gotta count your spots again like you did last year.
Left little 2, little 3, white spot. Yeah.
Oh, did I do that by accident?
Oh, yeah.
That my cousin told me.
Yeah. Who was your cousin? That's all that is. You're restricted for the graph to be shown. You're thinking it to be more difficult than it needs to be. Slope is -1. -1 slope goes down and right, or up and left. I went that direction because I knew I already looked at where my domain was at. I didn't bother graphing the other side. That's all. Because you're right. Normally I would graph down and right, but I knew that I'm looking going the other way, so I just went up and left. It was a preemptive strike, if you will. Real fast then, the easy ones. The step functions.
The easy one.
The step functions. The step functions usually wind up graphing multiple horizontal lines. You look really worried. Yes. Okay. Yeah, don't worry, guys. You're gonna be fine. Trust you remember this stuff.
I think he's telling us to worry, guys.
Not yet. You'll know when it's time to worry.
Oh, that's worrying.
It should be.
Wait.
Is that a threat or a promise?
Yes. The answer is yes. Whenever you have f of x equals a number or y equals a number, that is always, always, always a horizontal line. Whenever it's y equals some number, it's a horizontal line. Whenever it's x equals some number, it's a vertical line.
Okay.
When you have f of x equaling a number, f of x is synonymous, means kind of the same as y equals. So f of x equals 1 is a horizontal line that goes through 1. But I'm only going to graph that line between 0 and 1. Do I include or exclude 0? And do I include or exclude 1? I include 0 and I exclude 1. And there's just that little spot. Then it jumps to what? 2. And this is why it's called a step function. It steps up to 2 and goes to here. Remember I was talking about the age brackets? When you're X amount, you pay this much, then you pay this much, then you pay this much. Well, this is the same idea. If you are 1 year old, you pay $1. If you are 2, you pay 2. You pay your age to go to something. What do you got?
1, 2, 3, 4, those are y values, right? So like that means, no?
What do you mean? This is y equals 1. Y equals 2.
Then why did you go to 2? It's in between
When I'm graphing y equals 1, between the values of 0 and 1. Y equals 1 between 0 and 1. Remember, this is the domain part. This is the domain restriction.
So, the one you pick for
Remember, think of this in terms of y equals 1, graph it. And you only want that graph shown between 0 and 1. Y equals 2, that graph's only shown between 1 and 2. That's what we're doing. And it just changes itself through. And depending upon how the less than or equal to symbols are shown, sometimes they put the open dot on the first one, the solid dot on the second. A lot of times, and I completely forgot to do this, I should have made these steps longer. It's a little bit easier to see. But in essence, that's all this is, guys. It's that straightforward. Step ones are the easiest. Let me give you, I think I got like 8 or 9 problems for you to try tonight. It is on, it's section 2.7, obviously. Page 117, numbers 14 through 28 evens,
Oh my god.
and then 38 to 40. The 14 through 28, you got 4 problems there that are the f of x, g of x, what is f of 6, what is g of 7, that kind of thing. Then you have 4 graphs, so you use one of these little pieces of graph paper to graph them out. And then the last 3 are really cool. The last 3, you are going to write the equation given the step or the piece function.
Sounds so fun.
It's really easy because you have points. You're going to be able to walk your slopes. You're just going to write the equation given the values. Bless you. All right?
So